Chapter 2, Newton's Laws of Motion. Section 2.1, Newton's first law of motion. So in this chapter, we're going to talk a lot about Newton and his laws of motion. But before Newton, and even before Galileo, there was a man named Nicholas Copernicus. And the reason why he's important, especially as we talk about this part of the chapter, is because he was the first to posit the idea that the Earth was not the center of the universe or the center of the solar system at that time, because that's about all they could figure out. But instead, the sun was at the center, right? So Copernicus's idea was the heliocentric model of the solar system. Puts the sun at the center, and it allowed him to explain how the planets moved in the observed motion of planets like Mars. Now, in general, the way he described the motion of the planets was still wrong. But he figured out that the sun was the thing in the middle and not us. And what essentially comes about from that is the idea that Copernicus realized that if we're not the center of the if we're not the center of the universe, and the sun is, then we have to be moving around the sun. Which, if you sit on Earth, it doesn't feel like you're moving, but you are, right? So the Earth rotates relatively quickly. It revolves around the sun relatively quickly. The sun itself moves through the galaxy itself moves through the universe, and we're basically sitting on it, moving with it. We don't notice that motion because we can't see anything else moving beside us in the same way, right? So much like when we talked about it in the last chapter, if you're trapped on that plane and you can't see outside, there's no way to know that you're on a plane, right? There's no way for us to know that the Earth is moving unless we know something else about orbiting bodies and things like that. And so we're going to further those ideas, but it's important to at least discuss Copernicus at the beginning of this chapter. The other thing that's really important about Copernicus is he was one of the first people to try to go against this idea of the Earth being the center. And he happened to essentially die before anyone had any idea that he was right. So he didn't really get a chance to, he published his results close to his death, if I remember correctly. Okay, so the rest of this chapter is going to focus on one of the most important people in terms of physics, which is Isaac Newton. I invite you to please watch the video. That's just a brief biography about him that's attached with this with these notes. Isaac Newton contributed a lot to science in general. In addition to the laws of motion, laws of gravitation, calculus, optics, ideas with temperature, as we'll even see in a later chapter. There's lots of things that wind up having Newton's name on it. So he's really important in science. But his laws of motion, in general, may be one of the most important things that he did, because you can still use those laws now to talk about how things move. We can still solve problems using his laws. There are some things that Newton did, like the law of gravitation, that have been updated over time. But his laws of motion still essentially hold, so long as you're talking about regular-sized objects, or even in the case of planets, large-sized objects. But so long as you're dealing with things that are not microscopic and things that are not submicroscopic, then his laws of motion still work, and we still use them to solve problems. Now, the first law is essentially building off of what Galileo did. It's the idea that a force is required to change the motion of an object. Otherwise, it just keeps moving the same way that it always has. So Newton's first law is sometimes called the law of inertia, and basically just says that every object at rest will remain at rest, and every object in motion will remain in motion unless it's acted upon by a non-zero force, unless it's acted upon by a force. Okay, non-zero should be the obvious part. So what that means is if something's sitting still, it's going to keep sitting still until you touch it to move it, until you push it. And if something's moving, it's going to keep moving until something does something to stop it. We take advantage of this law when we talk about things like the Voyager satellite that is still traveling through the solar system. Actually, it's made it outside of the solar system in the past few years. It is beyond essentially the reach of the sun at this point. But that thing doesn't have, it was launched in, I think, the 70s or something like that. It doesn't have 30, 40 years worth of fuel on it. You just point it in one direction, get it going, and it'll keep going in that direction until something pulls on it, until some force acts on it. So the short version of Newton's first law is force is required to change the motion of an object. Otherwise, it's going to keep doing the same thing. Okay, so the other example you see here is baseball. Right? The pitcher throws the ball is going to keep traveling forward until the batter either hits it and applies a force to the ball, or the catcher catches it and the ball stops. Okay, so you require some force to change the motion of that ball. Okay, before the pitcher throws it, it's sitting at rest, and the pitcher applies a force to throw the ball. So in the next few sections, we'll discuss the last two laws of motion and how they'll essentially come together at the end.